koolwarm is a little computer code for thermal and simplified thermal hydraulics calculation. The main features are: it is written in C++ language, is based on finite difference discretization. Data are written on file of type text. Possibility for using Excel as pre and post processing exists. Data are managed by keyword. Thermal transfer modes are conduction, convection, radiation, internal and boundary condition, internal power and sink, and for flow circulation, fluid in natural convection, paths are supposed to be known, and the equilibrium between motric forces and pressure drop is achieved. Forced convection is also possible, so with known flow rate. Calculation of transfer coefficient is possible. It works for 2D geometry, RZ and XU. Material characteristics are function of temperatures. Some data are function of time, like power, flow, boundary temperature. Steady state and transient are calculated. Calculation example: we will consider 3 concentric tubes. On the internal tubes, also called element, power is installed in the central part. The intermediate tube, also called case, is filled with water, which flows by natural convection. The flow is up in the center of the element and down around the element. Between the external tubes called skirt and the case, air is blown in forced convection to cool the system. The case and the skirt exchange by radiation and natural convection. The shirts exchange also with ambient by radiation convection, its boundary. During transition, power is first increased and then it decreased. The blower flow decreased first and then increased again. The transition lasts about 1 hour. This is summarized on the scheme. Here is the internal tube or element. The central part here, where is the power. The case here is the intermediate tube, which is filled with water. The natural flow in the water is up in the center and down around the element. The skirt is here, and between the skirt and the case, air in forced convection is blown up toward down. Natural convection and radiation is applied to the shirt with ambient, it transfers with ambient, and radiation and convection is also set between the case and the shirt. Here is now an example for data preparation with Excel. Excel can help for definition and visualization of machine and also for automatic generation of some data. Here is a machine for the calculation we have chosen. Here is the central part of the element where the power is installed. Here is the water in the case. The case is here, and water is flowing up in the center of the element and around the element downward. This is in yellow the space between the case and the shirt where the air is blown to cool the overall system. The data are the following. First, there are general information, the number of regions, the geometry type, and also a lot of other numbers which are necessary. And we have, after the division for R and Z, and the region definition here. Initial temperatures are given, and also the power in the region. For example, here in 88 region number, we have set -1. That means that when the number is less than 0, means that it is a function number, the time function number. Then we have to define the connection between the region, and this is this type of definition. Boundary and internal radiation must be also provided, and this is we have also to give definition of forced convection, of natural convection zone, of also the region which are concerned for motrice force definition, material definition here, and also temperature function definition and time function definition. Now we look at the results, and the steady state needs about 9 iterations, and natural convection flow rate in water was found to be 0.4 kg per second, and temperatures are given here under, and you can see the maximum temperature in the hot part is 81 degrees, and the flow in the region which is cooled by airflow, temperature at inlet is 30 degrees and outlet 63 degrees. Water circulation in this part. So the hot part here and cool down here. Now tension. First, the time function which are given data. Here the power, which is increased at the beginning of the transient and after decreased quickly to be quite zero after 1000 seconds. Airflow rate is decreased at the beginning and then increase slowly up to the end of the tension. Temperature are given here. The hot region where the power is installed is here. And for the case here, and the skirt here. Here is the air inlet temperature, which is quite stable and equal to 30 degrees. And here is the outlet air temperatures. The flow rate in the natural circulation in water was found to be about 0.4 at the initial state. It increased very quickly with the power up to 1.2 kg per second, and then when the power decreased, it decreased also and increased a little at the end of the transient. The computational time for the steady state and for the 3000 seconds of the tension is about 60 seconds using the implicit method with a time step of about 1 second. The explicit method needs a smaller time increment, about 0.01 second, but the calculation time is about the same. In the code, we choose to activate only the implicit method. Next work will concern a 3D version and also a specific version adapted for system tension. Thank you for your attention. If you are interested, the email is this one.